Hi NAT aspirants, we have compiled three frames based on complex number. I have solved in lump sum 20 to 21 questions. After selecting from 100 questions, 2021, especially from KIPS manual, Federal Board past papers, the ample proof is that go and visit all these three videos available on my YTC as well as on my FB page. And here I am compelled to give you complex number tutorial. The things that have been used in all these questions mostly, and they are making trouble to define them. This is some sort of basic to learn some basic in order to attempt the questions on complex number. This video will facilitate your works to solve complex number as well as understand the three parts that we have solved for you. Without wasting time, I am starting from reverse fashion. All integrals powers of iota always results in 1 minus 1 iota minus iota. Whatever the power of iota is, iota raised to n, where n belongs to integers. N belongs to integers. Integers are 0, plus minus 1, plus minus 2, plus minus 3, and so on. It always results in these four numbers 1 minus 1 iota minus iota. Let's see how. If I put n is equal to 0, I will get 1. If I put 1, I will get iota. Okay, keep on doing something. Iota, it will become 1. Iota power 1, it's iota. Iota square, it's tantamount to minus 1. Iota cube can be written as iota square times iota. Iota square is minus 1. Minus 1 times iota, minus iota. What about iota 4? Iota 4 is iota square times iota square. Minus 1 times minus 1, it's positive 1. Now it keeps on repeating. Here look 1, here 1, the loop repeats. If I write iota 5 here, it will become how much? Iota 4 times iota. Iota 4 is 1, 1 times iota, it's my iota. Iota 6 can be written as iota 4 times iota square. Iota 4 1, iota square means minus 1, it will become minus 1. Similarly, iota power 7 can be written as iota power 4 into iota square into iota. Iota 4 is 1, iota square is minus 1 times iota, that's my minus iota, and so on. You can ask, you can object, so you have taken only the positive values. What about negative? They will also give the same results. 1 minus 1 iota minus iota, and belongs to a set of integers. I have taken positive one and I have proved. What about the negative values? Let's see and find out. Okay, iota raised minus 1 can be written as 1 over iota. Either you can rationalize. Okay, minus iota divided by minus iota. It will become minus iota upon minus iota square. Minus iota, value of iota square is minus 1. Minus plus, I am going to have minus iota. Okay, 1 upon iota square, it can negative already. Iota is minus 2, it can be written as 1 upon iota square. Iota square is equal to minus 1, I am going to get minus 1 again. Iota cube, negative cube, sorry, minus cube. It can be written as 1 over iota cube or 1 upon iota square times iota. That's iota square is equal to minus 1 times iota. It is minus 1 upon iota. If you can rationalize, you will arrive minus 1 upon iota divided and multiplied by iota. You will result minus iota divided by iota square, and minus iota divided by minus 1. Again, you are going to get iota. Similarly, take whatever you want. I am taking iota power 10. Iota is negative 10. It can be written as 1 upon iota power 10. It can be written as iota power 4 times iota power 4 times iota square. It will become 1 times minus 1. That is 1 over minus 1. Minus 1 is our result. Minus 1 is our result. So we have amply demonstrated whatever the value of n, if n belongs to integers, it always results in 1 minus 1 iota minus iota. That's the beauty of these four numbers. It is known as in abstract algebra the set of quaternions. The set of quaternions, and it's a wonderful in mathematical physics application. It is a group. It is a cyclic group under multiplication. It is a cyclic group under multiplication. The next our question is that we are about to prove. Now we have amply demonstrated that iota power n, where n belongs to z, they all results in 1 minus 1 iota minus iota. Let me prove that they are making a group. For a non-empty set to be a group requires four conditions. It must satisfy clear property, associative property, inverse, and identity. Without wasting time, I am giving you a good idea. Under multiplication, one is the identity. Good. Let me make the case table for you. Here it is 1 minus 1 iota minus iota. 1 minus 1 iota minus iota. Just multiply. 1 times 1 minus 1 iota minus iota. What about this? It will give us minus 1 positive 1 negative iota positive iota. It will give us iota minus iota. Iota into iota, iota square means minus 1. Iota into minus iota, it will become minus iota square. It will give us positive 1. Minus iota, it will give us positive iota, it will give us 1, it will give us minus 1. Look at this. Each element remain within that frame. It means it is closed. It is closed. It satisfies clear property. Similarly, it can satisfy associative property. Take any three elements in that fashion or in that fashion, then this you are going to get this. One is identity. It's clear. It's associative. What about inverse? Inverse of 1 is always 1. Inverse of identity is always identity. Inverse of minus 1, minus 1 raised minus 1 is minus 1 again. Inverse of 1 iota, it is 1 upon iota means minus iota. So inverse of iota is minus iota and inverse of minus iota is positive iota. So each element has inverse. Identity is there. It satisfies associative law. It satisfies clear property or binary operation. Yes, it is a group under multiplication. Second, it is a cyclic group. Cyclic group means all these elements can be generated by iota or minus iota. That I have just demonstrated before you. Whatever the power of iota where n belongs to z, it is 1 minus 1 iota minus iota. Okay. If I take iota, I can generate any element of this. If I want to generate 1, I write iota power 4. If I want to generate minus 1, I write iota star. If I want to write generate iota cube, then I will write iota cube means no. Iota cube, from where comes or occurs? Iota. Iota cube will give me minus iota. Okay. Iota 4 I can generate from 1 times iota or iota power 5. Iota power 5 means iota power 4 times iota, it's mine iota. So every element of this one can be generated by iota, similarly by minus iota, similarly by minus iota. So by virtue of this definition, all the elements of a group are generated by a single element. It is known as cyclic group. It is known as cyclic group. It is known as cyclic group, where 1 is identity, inverse of 1 is 1, inverse of minus 1 is minus 1, inverse of iota is minus iota, inverse of minus iota is iota. And we have amply demonstrated its clear, it's associative, it has identity, it has inverse. Each element has unique inverse, identity is unique, and so on. Similarly, here I have and another good question. The sum of four consecutive powers of iota always results in 0. Let's see and find out. Let me write iota m plus 1 taking four consecutive powers, m plus 2, their sum, iota raised m plus 3 plus iota raised m plus 4, they result in 0. Only four consecutive powers of iota. The sum of four consecutive powers of iota results in 0. I have taken where m is maybe negative, maybe positive, whatever iota it is, iota. Yes. According to tiny exponent rule, I can write iota raised m plus 1 as iota power m times iota power 1 plus iota times m, I can write iota square plus iota times m iota cube plus iota times m, iota raised m times iota 4. Okay, taking iota 4 iota raised m common. Sorry, iota raised m common. What remains? Iota plus iota square plus iota cube plus iota 4. Wonderful. Let it be iota power m. Iota square is equal to -1. Iota cube means iota square into iota 4 means iota square into iota square. Iota is m, iota minus plus minus. Iota square is also -1 times iota. Iota square means -1 into -1. Iota power m. We have iota minus iota. This is 1. Plus minus minus, it's by 1. Okay. 1 minus iota, minus minus plus 1. Look at this. Cancelled out, cancelled out. Iota raised m times 0. It is tantamount to 0. So, any 4 consecutive powers of iota, their sum always results in 0. Their sum always results in 0. Owing to the set of quaternions that I've already told you, iota raised n always results in 1, -1, iota, minus iota. If you are going to take 4 consecutive, you are going to get all these 3 in line. All these 3 in line, sum them, they are equal to 0. They are equal to 0. So we have done with this question as well. Second, multiplicative inverse of a complex number. Everybody is familiar. Everybody is familiar. So let's unearth this. Suppose our complex number is given by z is equal to a plus b iota. Multiplicative inverse, it can be written as 1 over a plus b iota. Whenever is iota present in denominator, rationalize by its conjugate. Rationalize by its conjugate. Conjugate means change the symbol of imaginary part, divide and multiply. This process is known as rationalization. Now we are finding multiplicative inverse of this one. 1 times a minus b iota. Here a plus b, a minus b, it can be written as a square minus b square iota square. A minus b iota, we are familiar. Iota square is equal to -1. Minus plus, so we have a minus b iota divided by a square plus b square. Writing the complex number in its shape, separating multiple real and imaginary parts. That's our real part, a divided by a square plus b square minus b over a square plus b square iota. Okay, that is the normal way of writing multiplicative inverse of a complex number. A plus b whole square minus b over a square plus b square. What to give you something new? What is a? What is a? That is real part divided by their magnitude square, means mod z square. And here it is negative times imaginary part divided by mod z square. Mod z square. This is the complex number. It can also be written in that fashion. In that fashion, if this sort of formula is written in that fashion, it is going to give you a jolt. It is going to give you a jolt. You should have idea what is this. A square plus b square. Yes, it's modulus of a complex number. Having no unknown means it's a square. This one can be written as this in order to prevent you from a shock. Okay, here you are familiar from this. Modulus of a complex number, its additive inverse, its conjugate, its additive inverse conjugate remains same. Conjugate of z, z bar, negative times z, negative times conjugate z, they all result in same. Let's see and find out. Or z means a plus b iota. Their magnitude is given by a square plus b square. By the way, from geometric point of view, it is known as distance of a complex number from origin. Distance of the complex number from origin as well. Or you can say that it is radius of the circle that represent that complex number. Mod z, mod z means a minus b iota. Finding their mod, it also results in a square plus negative b square. The magnitude of z bar is also same. Similarly, minus z means minus a minus b iota. Finding its conjugate, sorry, magnitude, negative a square, negative b square. We have positive a square plus b square. Similarly, additive inverse of the conjugate is given by minus a plus b iota. It will also result in minus a square plus b square. That is same. That is same. Good, quite cool. They also result same. They are all same. Now the wonderful application, the Nemo-Weyer's theorem of the name mathematician, hard to pronounce but easy to apply. Let's see and find out. Okay, let's prove this. Cos theta plus iota sin theta. Let us apply mathematical induction, 3 steps. And there's a twist in the tail as well, mathematical induction. Mathematical induction has 3 steps. Suppose it is true for m is equal to n. Step 1. Suppose it is true for m is equal to, put m here and here. We are going to get both sides equal. Cos theta plus iota sin theta raised 1 is equal to cos 1 theta plus iota sin 1 theta. They are equal. Cool. Step 1. Without wasting time, switch over to step 2. Suppose it is true for m is equal to k. Suppose it is true for m is equal to k. Right, instead of m, instead of mk, it will become cos theta plus iota sin theta raised k is equal to cos k theta plus iota sin k theta. Okay, for step 3, we need here, instead of k we need k plus 1. Suppose if we have a power k, if I want to get k plus 1, then I multiply with a. Bases are same, add their powers, a power k plus 1. If there is a raised k, I want this k to be with, if I want to enhance plus 1 in the power, I have to multiply with a, with the same base. So the trick works here by multiplying cos theta plus iota sin theta both sides. I have cos theta plus iota sin theta power k multiply cos theta plus iota sin theta power 1. It will become cos theta plus iota sin theta raised k plus 1. I have managed the left one, but our real target is how to settle this right hand side. It will become cos k theta plus iota sin k theta. Let me erase this and make a space for myself. Yes, just multiply on this side cos theta plus iota sin theta. Simply just multiply first term with both. It will become cos k theta times cos theta. This one with this, it will become cos k theta times iota sin theta. Cool. Now take iota sin theta and multiply with bracket iota sin k theta with cos theta plus iota sin k theta with iota. It will become iota square sin k theta sin theta. Okay, don't forget iota square is equal to -1. Replace this. They are the both numbers having iota. Take iota common from this, and our question is going to take shape. Cos k theta times cos theta plus taking iota common only, we have cos k theta sin theta plus sin k theta cos theta, and iota square is equal to minus 1. It is sin k theta sin theta. So this is our real part. This is also real part. Separating real and imaginary parts, the best study in complex numbers, we have cos k theta, cos theta, and here minus plus, it's minus sin k theta sin theta plus iota common, we have taken cos k theta sin theta plus sin k theta, that is cos theta. Now look at this. It's the famous identity cos alpha cos beta sin alpha sin beta. It can be merged as cos k theta minus theta, cos alpha cos beta minus sin alpha sin beta, cos alpha cos beta minus sin alpha minus sin beta. Minus means plus, basic trigonometry formula. Cos alpha plus beta is given by cos alpha cos beta minus sin alpha sin beta. It is merged as cos alpha plus beta, here minus here plus. In case of cos alpha cos beta minus sin alpha sin beta, it is equal to cos alpha plus beta, cos alpha plus beta. What about this? Plus iota sin, it is cos sin sin cos, sin alpha cos beta cos alpha sin beta. It is tantamount to sin alpha plus beta, sin alpha cos beta cos alpha sin beta. Let me write both the identities for you as well. That is sin alpha plus beta, it is equal to sin alpha cos beta plus cos alpha sin beta. Instead of this, we can write this. And similarly, cos alpha plus beta is given by cos alpha cos beta minus sin alpha sin beta. Instead of this, I have written this. That's the study here. If I take theta common from here and here, and it is our wonderful proof of complex de Moivre theorem regarding complex number. Theta common, we have k plus 1 plus iota sin. Theta common, here remains k plus 1. R1 can write in a good fashion as, this one can be written as cos k plus 1 theta plus iota sin k plus 1 theta. One can write as cis k1 k plus 1 theta. This is the proof of de Moivre's theorem. De Moivre's theorem. Or there is another trick. If you utilize Euler's identity, e raised to iota theta is equal to cos theta plus iota sin theta, then everything will become wonderful and simple. Wonderful and simple. Let's see how. That is e power iota theta is equal to cos theta plus iota sin theta. If it is raised to any power, e power iota theta power m, it will become e raised iota theta m. Utilizing this identity, we have cos m theta plus iota sin m theta. It's a wonderful replacement of a de Moivre's theorem. You can switch over to this identity and works. For example, we have given two complex numbers, cos m theta plus iota sin m theta, and we want to divide them, cos m theta plus iota sin m theta. To rationalize, to do this or that, stuck to this identity. It's a wonderful identity. Numerator can be written as e power iota m theta, and denominator can be written as e power iota m theta. Now, bases are same. I can write iota m theta times e raised negative iota m theta. As bases are same, add their powers. Bases are same, add their powers. It will become iota m theta minus iota m theta Taking iota and theta common, iota theta common, we have m minus n. R1 can write in same form, cos m minus n theta plus iota sine m minus n theta. It is a wonderful form to be utilized in order to deal with such questions easily avoiding de Moivre's theorem. De Moivre's theorem. It is tantamount to same thing. It is tantamount to de Moivre's theorem. But working with the power of E, working with the power of E will pave the way for your understanding. It will facilitate your calculation. It cuts your difficulty. It reduces your difficulty to more than 70%. Your calculation has been reduced owing to this formula. It's my tiny effort for you, net aspirants. Wait, what I have next for you. It's all by itself next.